System programmers may need to interact with OS-defined global values. Software that interacts with CPU registers and other low-level hardware needs to get used to inspecting flags to check that operations were completed successfully. The difference between const and let. If variables defined with let are immutable, then why does Rust include a const keyword? The short answer is that data behind let can change. Rust allows types to have an apparently contradictory property of interior mutability. Some types, such as stdsync.arc and stdrc.rc, present an immutable facade yet change their internal state over time. In the case of those two types, these increment a reference count as references to those are made and decrement that count when those references expire. At the level of the compiler, let relates more to aliasing than immutability. Aliasing, in compiler terminology, refers to having multiple references to the same location in memory at the same time. Read-only references, or borrows, to variables declared with let can alias the same data. Read-write references, or mutable borrows, are guaranteed to never alias data. Section 3.4.2. Making use of the result return type. Rust's approach to error handling is to use a type that stands for both the standard case and the error case. This type is known as result. Result has two states, OK and error. This two-headed type is versatile and is put to work all through the standard library. We'll consider how a single type can act as two later on. For the moment, let's investigate the mechanics of working with it. Listing 3.8 makes changes from previous iterations. Functions that interact with the file system, such as open on line 39, return result of file and string. This effectively allows two types to be returned. When the function successfully executes, file is returned within a wrapper as OK file. When the function encounters an error, it returns a string within its own wrapper as error of string. Using a string as an error type provides an easy way to report error messages. Calling functions that return result of file and string requires an extra method, unwrap, to actually extract the value. The unwrap call unwraps OK file to produce file. It will crash the program if it encounters error string. More sophisticated error handling is explained in Chapter 4. Open and close now take full ownership of their file arguments. While we'll defer to a full explanation of the term ownership until Chapter 4, it deserves a short explanation here. Rust's ownership rules dictate when values are deleted. Passing the file argument to open or close without prepending an ampersand, e.g. ampersand file or ampersand mute file, passes ownership to the function that is being called. This would ordinarily mean that the argument is deleted when the function ends, but these two also return their arguments at the end. The F4 variable now needs to reclaim ownership. Associated with the changes to the open and close functions is a change to the number of times that let F4 is used. F4 is now rebound after each call to open and close. Without this, we would run into issues with using data that is no longer valid. To run the code in listing 3.8, execute these commands from a terminal window. To do things by hand, here are the recommended steps. 1. Move to a scratch directory, such as /tmp. For example, cd $tmp, cd %tmp% on MS Windows. 2. Execute cargo new --bin --bcs non-file result. 3. Ensure that the crates cargo.toml file specifies the 2018 edition and includes the rand crate as a dependency. 4. Replace the contents of file result /src/main.rs with the code in listing 3.8. ch3/file result /src/main.rs. 5. Execute cargo run. Executing cargo run produces debugging output, but nothing from the executable itself. Note: calling .unwrap on a result is often considered poor style. When called on an error type, the program crashes without a helpful error message. As the chapter progresses, we'll encounter sophisticated mechanisms to handle errors. Using result provides compiler-assisted code correctness. Your code won't compile unless you've taken the time to handle the edge cases. This program will fail on error, but at least we have made this explicit. So what is a result? Result is an enum defined in Rust's standard library. It has the same status as any other type, but is tied together with the rest of the language through strong community conventions. You may be wondering, wait, what is an enum? I'm glad you asked. That's the topic of our next section. Section 3.5, Defining and Making Use of an Enum. An enum, or enumeration, is a type that can represent multiple known variants. Classically, an enum represents several predefined known options like the suits of playing cards or planets in the solar system. The following listing shows one such enum. If you haven't programmed in a language that makes use of enums, understanding their value takes some effort. As you program with these for a while, though, you're likely to experience a minor epiphany. Consider creating some code that parses event logs. Each event has a name, perhaps update or delete. Rather than storing those values as strings in your application, which can lead to subtle bugs later on when string comparison becomes unwieldy, enum allows you to give the compiler some sense of the event codes. Later, you'll be given a warning such as, "Hi there, I see you have considered the update case, but it looks like you've forgotten the delete case. You should fix that." Listing 3.10 shows the beginnings of an application that parses text and emits structured data. When run, the program produces the following output. You'll find the code for this listing in ch3/ch3-parse-log.rs. Enums have a few tricks up their sleeves. These work together with Rust's pattern matching capabilities to help you build robust, readable code. Visible on lines 19 through 23 of listing 3.10. Like structs, enums support methods via IMPL blocks. Rust's enums are more powerful than a set of constants. It's possible to include data within an enum's variants, granting them a struct-like persona. For example, Section 3.5.1, using an enum to manage internal state. Now that you've seen how to define and use an enum, how is this useful when applied to modeling files? We can expand our file type and allow it to change as it's opened and closed. Listing 3.11, ch3/ch3-file-states.rs, produces code that prints a short alert to the console. Enums can be a powerful aid in your quest to produce reliable, robust software. Consider them for your code when you discover yourself introducing stringly typed data, such as message codes. Section 3.6, Defining Common Behavior with Traits. A robust definition of the term file needs to be agnostic to storage medium. Files support two main operations, reading and writing streams of bytes. Focusing on those two capabilities allows us to ignore where the reads and writes are actually taking place. These actions can be from a hard disk drive, an in-memory cache, over a network, or via something more exotic. Irrespective of whether a file is a network connection, a spinning metal platter, or a superposition of an electron, it's possible to find rules that say, to call yourself a file, you must implement this. You have already seen traits in action several times. Traits have close relatives in other languages. These are often named interfaces, protocols, type classes, abstract base classes, or perhaps contracts. Every time you've used this in a type definition, you've implemented the debug trait for that type. Traits permeate the Rust language. Let's see how to create one. Section 3.6.1. Creating a read trait. Traits enable the compiler, and other humans, to know that multiple types are attempting to perform the same task. Types that use this all print to the console via the println! Macro and its relatives. Allowing multiple types to implement a read trait enables code reuse and allows the Rust compiler to perform its zero-cost abstraction wizardry. For the sake of brevity, listing 3.12 at this link is a bare-bones version of the code that we've already seen. It shows the distinction between the trait keyword, which is used for definitions, and the IMPL keyword, which attaches a trait to a specific type. When built with Rust C and executed, listing 3.2 prints the following line to the console. Defining a trait and implementing it on the same page can feel quite drawn out in small examples such as this. File is spread across 3 code blocks within listing 3.12. The flip side of this is that many common traits become second nature as your experience grows. Once you've learned what the partial EQ trait does for one type, you'll understand it for every other type. What does partial EQ do for types? It enables comparisons with the equals operator. Partial allows for cases where two values that match exactly should not be treated as equal, such as the floating point's nan value or sequel's null. Note: if you spent some time looking through the Rust community's forums and documentation, you might have noticed that they've formed their own idioms of English grammar. When you see a sentence with the following structure, T is debug, what they're saying is that T implements the debug trait. Section 3.6.2. Implementing standard FMT display for your own types. The println! Macro and a number of others live within a family of macros that all use the same underlying machinery. The macros println! Print! Write! Write ln! And format! all rely on the display and debug traits, and these rely on trait implementations provided by programmers to convert from open-close curly braces to what is printed to the console. Looking back a few pages to listing 3.11, the file type was composed of a few fields and a custom subtype, file state. If you recall, that listing illustrated the use of the debug trait as repeated in the following listing. It's possible to rely on the debug trait auto-implementations as a crutch, but what should you do if you want to provide custom text? Display requires that types implement a FMT method, which returns FMT result. The following listing shows this implementation. The following listing shows how to implement display for a struct that includes fields that are also needed to implement display. You'll find the code for this listing in ch3/ch3-implementing-display.rs. We'll see many uses of traits throughout the course of the book. These underlie Rust's generic system and the language's robust type checking. With a little bit of abuse, these also support a form of inheritance that's common in most object-oriented languages. For now, though, the thing to remember is that traits represent common behavior that types opt into via the syntax IMPL trait for type. Section 3.7. exposing your types to the world. Your crates will interact with others that you build over time. You might want to make that process easier for your future self by hiding internal details and documenting what's public. This section describes some of the tooling available within the language and within Cargo to make that process easier. Section 3.7.1 Protecting Private Data. Rust defaults to keeping things private. If you were to create a library with only the code that you've seen so far, importing your crate would provide no extra benefit. To remedy this, use the pub keyword to make things public. Listing 3.16 provides a few examples of prefixing types and methods with pub. As you'll note, its output is not very exciting. Section 3.8 Creating inline documentation for your projects. When the software systems become larger, it becomes more important to document one's progress. This section walks through adding documentation to your code and generating HTML versions of that content. In listing 3.17, you'll see the familiar code with some added lines beginning with / or / exclamation point. The first form is much more common. It generates documents that refer to the item that immediately follows. The second form refers to the current item as the compiler scans the code. By convention, it is only used to annotate the current module, but is available in other places as well. The code for this listing is in the file ch3-file-doct.rs. Section 3.8.1 Using RustDoc to render docs for a single source file. You may not know it, but you also installed a command line tool called RustDoc when you installed Rust. RustDoc is a special purpose Rust compiler. Instead of producing executable code, it produces HTML versions of your inline documentation. Here is how to use it. Assuming that you have the code from listing 3.17 saved as ch3-file-doc.rs, follow these steps. 1. Open a terminal. 2. Move to the location of your source file. 3. Execute rustdoc ch-file-doc.rs. RustDoc creates a directory, doc/ for you. The documentation's entry point is actually within a subdirectory, doc/ch_file_doc/index.html. When your program starts to get larger and span multiple files, invoking RustDoc manually can become a bit of a pain. Thankfully, Cargo can do the grunt work on your behalf. That's discussed in the next section. Section 3.8.2 Using Cargo to render docs for a crate and its dependencies. Your documentation can be rendered as rich HTML output with Cargo. Cargo works with crates rather than the individual files as we've worked with so far. To get around this, we'll move our project into a crate documentation. To manually create the crate, follow these instructions. 1. Open a terminal. 2. Move to a working directory such as /tmp/ or for Windows, type cd %temp%. 3. Run Cargo new file basics. You should end up with a project directory tree that looks like this. 4. Now save the source code from listing 3.17 to file basics /src/main.rs, overwriting the Hello World boilerplate code that is already in the file. To skip a few steps, clone the repository. Execute these commands from a terminal. To build an HTML version of the crate's documentation, follow these steps. 1. Move to the project's root directory, file basics /, which includes the cargo.toml file. 2. Run cargo doc --open. Rust will now start to compile an HTML version of your code's documentation. You should see output similar to the following in the console. If you added the --open flag, your web browser will automatically open. Figure 3.4 shows the documentation that should now be visible. Tip: if you have lots of dependencies in your crate, the build process may take a while. A useful flag is cargo doc --no -deps. Adding --no deps can significantly restrict the work RustDoc has to do. RustDoc supports rendering rich text written in Markdown. That allows you to add headings, lists, and links within your documentation. Code snippets that are wrapped in triple backticks are given syntax highlighting. Summary: a struct is the foundational compound data type. Paired with traits, structs are the closest thing to objects from other domains. An enum is more powerful than a simple list. Enum's strength lies in its ability to work with the compiler to consider all edge cases. Methods are added to types via IMPL blocks. You can use global error codes in Rust, but this can be cumbersome and generally is frowned on. The result type is the mechanism the Rust community prefers to use to signal the possibility of an error. Traits enable common behavior through Rust programs. Data and methods remain private until they are declared public with pub. You can use cargo to build the documentation for your crate and all of its dependencies. Chapter 4. Lifetimes, Ownership, and Borrowing. This chapter covers discovering what the term lifetime means in Rust programming, working with the borrow checker rather than against it, multiple tactics for dealing with issues when these crop up, understanding the responsibilities of an owner, learning how to borrow values that are owned elsewhere. This chapter explains one of the concepts that trip up most newcomers to Rust. It's borrow checker. The borrow checker checks that all access to data is legal, which allows Rust to prevent safety issues. Learning how this works will, at the very least, speed up your development time by helping you avoid run-ins with the compiler. More significantly, though, learning to work with the borrow checker allows you to build larger software systems with confidence. It underpins the term fearless concurrency. This chapter will explain how this system operates and help you learn how to comply with it when an error is discovered. It uses the somewhat lofty example of simulating a satellite constellation to explain the trade-offs relating to different ways to provide shared access to data. The details of borrow checking are thoroughly explored within the chapter. However, a few points might be useful for readers wanting to get quickly to the gist. Borrow checking relies on three interrelated concepts: lifetimes, ownership, and borrowing. Ownership is a stretched metaphor. There is no relationship to property rights. Within Rust, ownership relates to cleaning values when these are no longer needed. For example, when a function returns, the memory holding its local variables needs to be freed. Owners cannot prevent other parts of the program from accessing their values or report data theft to some overarching Rust authority. A value's lifetime is the period when accessing that value is valid behavior. A function's local variable lives until the function returns. Well, global variables might live for the life of the program. To borrow a value means to access it. This terminology is somewhat confusing as there is no obligation to return the value to its owner. Its meaning is used to emphasize that while values can have a single owner, it's possible for many parts of the program to share access to those values. Section 4.1. Implementing a mock CubeSat ground station. Our strategy for this chapter is to use an example that compiles. Then, we'll make a minor change that triggers an error that appears to emerge without any adjustment to the program's flow. Working through the fixes to those issues should make the concepts more complete. The learning example for the chapter is a CubeSat constellation. If you've never encountered that phrase before, here are some definitions. CubeSat, a miniature artificial satellite, as compared to a conventional satellite that has increasingly expanded the accessibility of space research. Ground station, an intermediary between the operators and the satellites themselves. It listens on a radio, checking the status of every satellite in the constellation and transmitting messages to and fro. When introduced in our code, it acts as the gateway between the user and the satellites. Constellation, the collective noun for satellites in orbit. Figure 4.1 shows several CubeSats orbiting our ground station. In Figure 4.1, we have 3 CubeSats. To model this, we'll create a variable for each. This model can happily implement integers for the moment. We don't need to model the ground station explicitly because we're not yet sending messages around the constellations. We'll admit that model for now. These are the variables. To check on the status of each of our satellites, we'll use a stub function and an enum to represent potential status messages. The check_status function would be extremely complicated in a production system. For our purposes, though, returning the same value every time is perfectly sufficient. Pulling these 2 snippets into a whole program that checks our satellites twice, we end up with something like the following listing. You'll find this code in this file. Running the code in listing 4.1 should be fairly uneventful. The code compiles, albeit begrudgingly. We encounter the following output from our program. Section 4.1.1, encountering our first lifetime issue. Let's move closer to idiomatic Rust by introducing type safety. Instead of integers, let's create a type to model our satellites. A real implementation of a CubeSat type would probably include lots of information about its position, its RF frequency band, and more. In the following listing, we'll stick with only recording an identifier. Now that we have a struct definition, let's inject it into our code. The next listing will not compile yet. Understanding the details of why it won't is the goal of much of this chapter. The source for this listing is in this file. When you attempt to compile the code for listing 4.3, you'll receive a message similar to the following, which has been edited for brevity. To trained eyes, the compiler's message is helpful. It tells us exactly where the problem is and provides us with a recommendation on how to fix it. To less experienced eyes, it's significantly less useful. We are using a moved value and are fully advised to implement the copy trait on CubeSat. Huh? It turns out that although it is written in English, the term move means something very specific within Rust. Nothing physically moves. Movement within Rust code refers to movement of ownership rather than the movement of data. Ownership is a term used within the Rust community to refer to the compile time process that checks every use of a value is valid and that every value is destroyed cleanly. Every value in Rust is owned. In both listings 4.1 and 4.3, sat_A, sat_B, and sat_C own the data that these refer to. When calls to check_status are made, ownership of the data moves from the variables in the scope of main to the variable sat_ID within the check_status function. The significant difference is that listing 4.3 places that integer within a CubeSat struct. This type change alters the semantics of how the program behaves. Footnote 1. Remember the phrase zero-cost abstractions? One of the ways this manifests is by not adding extra data around values within structs. The next listing provides a stripped-down version of the main function from listing 4.3. It is centered on sat_a and attempts to show how ownership moves from main into check_status. Rebinding is legal when values are not borrowed. If you have experience with programming languages such as JavaScript from 2015 onward, you may have been surprised to see that the variables for each of the CubeSats were redefined in listing 4.3. In that listing, on line 20, a_status is assigned to the result of the first call to check_status of sat_a. On line 26, it is reassigned to the result of the second call. The original value is overwritten. This is legal Rust code, but one must be aware of ownership issues and lifetime here too. It's possible in this context because there are no live borrows to contend with. Attempting to overwrite a value that's still available from elsewhere in the program causes the compiler to refuse to compile your program. Figure 4.2 provides a visual walkthrough of the interrelated processes of control flow, ownership, and lifetimes. During the call to check_status of sat_a, ownership moves to the check_status function. When check_status returns a status message, it drops the sat_a value. The lifetime of sat_a ends here. Yet, sat_a remains in the local scope of main after the first call to check_status. Attempting to access that variable will incur the wrath of the borrow checker. The distinction between a value's lifetime and its scope, which is what many programmers are trained to rely on, can make things difficult to disentangle. Avoiding and overcoming this type of issue makes up the bulk of this chapter. Figure 4.2 helps to shed some light on this. Section 4.1.2 Special Behavior of Primitive Types. Before carrying on, it might be wise to explain why listing 4.1 compiled at all. Indeed, the only change that we made in listing 4.3 was to wrap our satellite variables in a custom type. As it happens, primitive types in Rust have special behavior. These implement the copy trait. Types implementing copy are duplicated at times that would otherwise be illegal. This provides some day-to-day convenience at the expense of adding a trap for newcomers. As you grow out from toy programs using integers, your code suddenly breaks. Formally, primitive types are said to possess copy semantics, whereas all other types have move semantics. Unfortunately, for learners of Rust, that special case looks like the default case because beginners typically encounter primitive types first. Listing 4.5 and 4.6 illustrate the difference between these two concepts. The first compiles and runs, the other does not. The only difference is that these listings use different types. The following listing shows not only the primitive types but also the types that implement copy. The following listing focuses on those types that do not implement the copy trait. When used as an argument to a function that takes ownership, values cannot be accessed again from the outer scope. Section 4.2 Guide to the figures in this chapter. The figures used in this chapter use a bespoke notation to illustrate the three interrelated concepts of scope, lifetimes, and ownership. Figure 4.3 illustrates this notation. Section 4.3. What is an owner? Does it have any responsibilities? In the world of Rust, the notion of ownership is rather limited. An owner cleans up when its value's lifetimes end. When values go out of scope or their lifetimes end for some other reason, their destructors are called. A destructor is a function that removes traces of the value from the program by deleting references and freeing memory. You won't find a call to any destructors in most Rust code. The compiler injects that code itself as part of the process of tracking every value's lifetime. To provide a custom destructor for a type, we implement drop. This typically is needed in cases where we have used unsafe blocks to allocate memory. Drop has one method, shown here, that you can use to conduct any necessary windup activities. An implication of this system is that values cannot outlive their owner. This kind of situation can make data structures built with references, such as trees and graphs, feel slightly bureaucratic. If the root node of a tree is the owner of the whole tree, it can't be removed without taking ownership into account. Finally, unlike the Lockean notion of personal property, ownership does not imply control or sovereignty. In fact, the owners of values do not have special access to their owned data, nor do these have the ability to restrict others from trespassing. Owners don't get a say on other sections of code borrowing their values. Section 4.4. How ownership moves. There are two ways to shift ownership from one variable to another within a Rust program. The first is by assignment. The second is by passing data through a function barrier, either as an argument or a return value. Revisiting our original code from listing 4.3, we can see that sat_a starts its life with ownership over a CubeSat object. Footnote 2. Within the Rust community, the term variable binding is preferred because it's more technically correct. The CubeSat object is then passed into check_status as an argument. This moves ownership to the local variable sat_id. Another possibility is that sat_a relinquishes its ownership to another variable within main. That would look something like this. Lastly, if there's a change in the check_status function signature, it too could pass ownership of the CubeSat to a variable within the calling scope. Here is our original function. And here is an adjusted function that achieves its message notification through a side effect. With the adjusted check_status function used in conjunction with a new main, it's possible to send ownership of the CubeSat object back to their original variables. The following listing shows the code. Its source is found in ch4/ch4-check-sats-3.rs. The output from the new main function in listing 4.7 now looks like this. Figure 4.4 shows a visual overview of the ownership movements within listing 4.7. Section 4.5. Resolving ownership issues. Rust's ownership system is excellent. It provides a route to memory safety without needing a garbage collector. There is a but, however. The ownership system can trip you up if you don't understand what's happening. This is particularly the case when you bring the programming style from your past experience to a new paradigm. More general strategies can help with ownership issues. Use references where full ownership is not required. Duplicate the value. Refactor code to reduce the number of long-lived objects. Wrap your data in a type designed to assist with movement issues.